Okay, good morning to all. So we were discussing about equivalent norms. The definition that we have given is that if two nonlinear spaces on the same vector space, you have two different norms. And we say that these two norms are equivalent if the induced metric creates the same topology. And then we have seen which is equivalent to saying so what we said is the induced metric topology is same. And which turned out to be saying the following, that if you can find out two constants, say C1 and C2, such that for all x in the space X, this inequalities C1 times norm x1 is less than 2 norm of this, which is less than C2 times. Okay. If this happens, note that this, though we are written as it is a two sets of inequality. C1 x1 times C1 times norm x1 is less than or equal to norm x2, and then other part. So this is one inequality, and this is another inequality. And right now we have proved this state, saying this is same as saying that. That's what we said. So now we look at few examples. Let's consider Rn. Let's say 1 norm and the same space with infinite norm. Now, because of the second inequality, this equivalent statement, it is enough if we check for the constant C1 and C2 in the case of nonlinear space. And is there any choices for C1 and C2? Can you think of some easy choices for C1 and C2? So what is the 1 now? It is summation of all the coordinates. And what is infinite norm? It is maximum of the coordinates, of course with the absolute value. So what is the immediate? Look at each of these inequality. Yeah, so how many of you have the answer? You can say yes. Yeah, Himanshu?
Sir, we can take the first norm to be the sup norm and the second norm to be the.
I'm able to hear you. Just hold on. Are you saying?
Hello, yes, sir. Hello. Hello. Sir, can you hear me? Sir, we can take this the first norm to be the sup norm.
Okay.
And the second norm to be the 1 norm. So,
okay.
Like C1 can be 1 only.
Okay. So all that you are saying is this. This is less than or equal to this.
This is less than or equal to n times of the sup norm.
Okay, so this you might have, and we are saying that this is less than or equal to n times. Okay. So check that in this case it is easy. Okay. Right. So what are the constants anyway? The C1 is 1 and the C2 is n. So as a second example, how about comparing an Rn? 1 norm and let's say 2 norm. Yeah, how many of you answered for this? Or if it is difficult, maybe I will change it. How about say 2 norm and infinite norm? So what is 2 norm? It is this. This is the 2 norm. And you know what is infinite. Okay. I want you to go through this kind of simple inequality in your mind. All the time, first let us try whether it works out or not. Okay. What is the direct comparison? Xi, if I consider 1. So each of the xi has to be less than or equal to this maximum. So I can replace inner things by the maximum of xi or the infinite norm of that. And so the squares of that. So such things are n. So n times of such squares. And then I have to take the square root. So it'd be square root of n into this norm. Are you able to follow this inequality now, what I said? Straight. Okay. So are you able to see this fact then? You will get each place you are replacing. Maybe I'll write once. I want you to see these things quickly. Okay. This is fine. Each place I can write norm xi replaced by this, and which is less than. If there are n such terms, so it will be n times actually equality. And look at this is nothing but square root of n into this. So at least we could get one side. Now x2 is less than or equal to square root of n times x infinity. Now I need to, so one side I got it. I would try to do the other way. Is it clear that how do you do the other way? Yeah. Yeah, Deepanjana?
Yes, sir. Constant will be 1. Means norm infinity less than norm 2.
Yeah, so it's direct. That's what you're
Yes.
saying. Okay, so check this. You have seen number of other things. So, and hence, what is that we are concluding? So, by the first example, one norm and infinite norm on Rn are equivalent. And by this, we can say that now these two are also equal. So, these are equivalent. And this is something that you have seen number of times in other, possibly other courses also. May not be in the same language, but you might have done this. So obviously there is another pair we can ask, which is what about norm 1 and norm infinite? Sorry, norm 2. Okay, I urge you to check this, and if needed, you try to use directly. Also try to get some estimate, or also use Cauchy Schwarz. Okay, so I give you as exercise. Two types. So you directly get the constant. Another one, use Cauchy Schwarz. You want, because one of them is 2 norm. So you know there is a Cauchy Schwarz you can use, or Holder's more general. Holder's inequality also you can use, and to get that. But we need to answer. We want to answer this in a different way. For example, now I say that if I create, once I observe the following. So if I say that 2 norms are equivalent is the definition I've given. If it is also true that these norms being equivalent is an equivalence relation, then I get this 3 using 1 and 2. Is it clear? So if I prove this norm equivalence is an equivalence relation. So this is an equivalence relation on set of all norms. So norm being equivalent, okay. This is an equivalence relation on norms on X. Okay, if once you fix the space, you collect all the norms, that actually creates an equivalence relation, and hence you will have equivalence class also. I give you just take 15 seconds to go through that it is actually an equivalence relation. So what I need to check whether norm is equivalent to itself. If norm 1 is, that is a reflexive, and norm 1 is equivalent to norm 2, is it true that norm 2 is also equivalent to norm 1? And if norm 1 is equivalent to norm 2, and norm 2 is equivalent to norm 3, then norm 1 and norm 3 are also equivalent. Okay. Okay, for reflexive, is it easy? How many of you could see the proof immediately? Means every time you need to produce that C1, C2, remember. For reflexive, I can use the same C1 and C2. For symmetry, note that the constants, you will take the inverse of those constants will help. And to prove the transitivity, you have to play with the inequalities. Play with the inequality means A less than or equal to B, B less than or equal to C. That way you have to write it. Okay, and you will get it. Okay, I'll leave this as again as an exercise. You can check it. It's very easy. See, once you understood that this is an equivalence relation, the third is answered very immediately. Okay, so these two are also equivalent. So they are. We know number of sequence spaces. Okay, remember the equivalent we can speak on the same space. Okay. And among the LP spaces, we know this is the smallest one. We have said C0, which is inside all LP spaces, and which is inside your sequence which are converging to 0, and then sequence which are just converging, and then sequence which are bounded. So I'll restrict now myself to only this and ask the following question. Remember, what are the norms on these spaces? On LP, norm P norm is the norm, and on and C naught and C, in L infinity, it is the infinite norm. Question that we are asking is that we already know that on a bigger space, if we have some norm, you can always bring that to the smaller subspaces. And hence, look at C naught, you can define all kinds of norms. That is, all LP norms can be defined on C naught naught, and L infinity norm also can be defined on C naught naught. And so I'll ask the same question now. So on C naught naught, can I compare this one norm and let's say infinite norm? So can you think of an answer? If you know you got something, then you can say that. If you want, I can show this. See, in Rn, we looked at the first one norm and infinite norm. See that whether anything of such helps. Yeah, Datta?
We can use the same thing that we used in Rn. Like C naught naught is essentially Rn followed by some zeros. We
Yes.
need not worry about those zeros at all.
Okay.
So infinity norm is less than 1 now.
Okay, so I'm writing. So what you're saying is that infinite norm is less than or equal to 1 now. All of you agree? I'm just... Okay. So this part is fine. Now what about the other part, Datta?
There is one such value, but
Okay. So how many of you think the other one we can create? So we can find out C2 such that norm of x1 is less than or equal to C2 times norm x infinity. How many of you think we can find out C2? Yeah, Jayant?
So can we take
No.
C1 as 0?
C1 as 0?
Yeah. Or they
No.
both should be positive.
Yes, yes. No, both are positive. We are finding strictly positive numbers. Yes. By definition, it will be. Yeah. So what about others? No idea what to be done. It's right that so it is not true. In that way, we can at least the example in R1 says that it's some n depends on Rn, and so this n has to be as big as possible. And so we may think that it is not working out. That's a correct line of thought, but we have to make it very precise. So we want to say now that you cannot find out any such constant C2. It's such that it is satisfying this. So what is the meaning of that? We are actually trying to find out there exists some C2 such that for all x in x, we are trying to find out norm x1 is less than or equal to C2 times norm x infinity. And we are saying that this may not work out, which is same as saying that you given any C2, I should be able to produce an x in x such that this does not satisfy this property, which is strictly bigger than C2 times norm x infinity. So all it says is that if you give me any C2, I should be able to produce an X such that this inequality is true. That means the above inequality is not true. This is what I need to do. Okay, to say that it is, we cannot find out such a C2. And notice that this is the way that we will try out whenever we want to say that two norms are not equivalent. In fact, one can even simplify this instead of looking at this is again a standard thing in analysis that you do. First thing is, we will not look for all C2. We will look for the following. Just say that. So if I show that for all natural numbers n, if I can produce an x in x such that this norm x1 is bigger than n times, can you say that this is sufficient to prove the last statement is sufficient to say the previous statement? How many of you agree? Good. Why is that? Suppose if I have the third statement, and if you give me any C2, now I can use, I can always find out a natural number such that this natural number is bigger than C2, and I can show this, okay, whatever you want, right? If I can show this itself is true, C2 will be smaller than that. So C2 times norm x infinity also bigger than norm x1, you will get it. Right, I'm clearing that. So this is the first. So instead of proving the second one, we may try to prove the third one. And if the third one also, now what I need to look at, if you give me any natural number n, any natural number, I need to produce an x from the space such that one norm of x is something and n times of the other norm. So the better way to deal this kind of inequality is that I choose an x such that which is easy for me to fix one of them. Okay, maybe I will choose an x such that the infinite norm of x is say 1, or one norm of x is say 1. Like that, if I fix it, then I'm trying to look at only playing with the other norm. So we assume sometimes, not assume, to make, remember we need to check that this is not true. That's what we need to do. And hence I try to find out an x such that x is either this norm is 1, which is easy to calculate, or this norm is 1. Then I'm just planning with, suppose if this norm is 1, all that I'm trying to find is, I'm finding an x such that now one norm of x is bigger than n. That's what I will try to do. So let's come back to this case now very specifically. What I'm saying, what I was saying here is it clear now? So you give me an x, given any natural number, can you think of an x for which one norm finding is easy or infinite norm finding is easy? It's clear that infinite norm finding is possibly. Thinking of sequences whose one norm is 1, that means summation has to be 1. So it is difficult. Whereas one norm of infinite norm of a sequence, if I give you, I need to find out only the maximum. And so can you think of like this? And it satisfies this. Yeah. Now, what are the elements whose infinite norm is 1 in the case of sequences in C0? That's standard. Yeah, Gaurav?
1 0 0 0 0.
Okay. So 1 0 0, if I take the infinite norm is 1, what about the one norm of that? Gaurav, what is the one norm of that element, whatever you said?
That is also 1.
But I want that to be bigger than n. I'm looking for an x whose infinite norm is 1, but one norm is bigger than n.
Okay, then we can take n plus 1 0 0 0.
What is that? Repeat.
N plus 1 0 0 0.
No, but what is the infinite norm of that? That will be n plus 1, no?
Yes, yes.
But I want infinite norm to be 1. Yeah, Nikhil?
we can take the first n plus 1 terms as 1 and rest are zeros.
That's it. That's it. So take x equal to, it's a sequence, remember, so it is 1 1 1 1, maybe n plus 1 times, and after that 0. So this is a point I want to make sure that thinking that yes, this will not work out. One can actually see from this, in Rn case, this right hand side is n, let's say. So in the case of Rn case, the right hand side is n, and sequence is something like infinity, infinite copies of r, and so this n may not be there. But that's just an intuition. That doesn't say, that is not the precise way of dealing it. That's only gives you an idea. But here it gives a precise idea. Now take this element. Now whatever n if you give, I will choose x as this. And then the infinite norm of this will be 1. And one norm of this will be n plus 1, which satisfies this. And hence we are proving that this norm is not equivalent. In fact, what we have, what we get is in the two parts of, there are two parts of inequality, as I have put here, these two brackets. So one part we are getting and another part we are not getting. That's what is happening. Okay. But if, unless we get both parts, it's not equivalent. So these two norms are not equivalent. Now I will urge you to check what happens to other norms. You can take one norm, two norm, p norm, one with norm with p norm, one with norm with infinite norm. So those are all exercises. So I'll write maybe. So check other p norms equivalence. I will ask a question that on a subspace, if two norms are not equivalent, on a bigger space, can it be equivalent? Is the question clear? X is the original norm in a space, and there are two norms, norm 1 and norm 2, and Y is a subspace of X. And on Y, these norm 1 and norm 2 are not equivalent. Can it be equivalent on the bigger space? Right. So some of you are getting it. It's clear. See, for each of this n, you are producing an x. In the subspace Y itself, if you can produce this x, it's there in the bigger space also to violate this. Okay. And hence, right. So in C0 itself, if you can show that these p norms are not equivalent, then you can very well think that on L1, if you consider one norm and two norm, they cannot be equivalent. Okay. Because on a smaller space itself, it is not equivalent. Let's okay, go ahead. Another example. I'm considering say C01. This is a space that set of all continuous functions on 0, 1. There are two norms that we have defined. One is one norm, which is defined as integration. And another norm, which we defined as sup norm. Or in this case, x is 0, 1. Yeah. Now, can you think of, are they equivalent? I give you a minute. Think about it. So if you get any one side of the inequality, you can say yes. Yeah, Namachivayam.
He said one norm is less than or equal to infinity.
So one norm is less than or equal to infinity norm. So what is this geometrically we have done? What is the one norm? It is the integration of a function. So if I consider this is 0, 1 and I have a function. Okay, so this is my f of x. Of course, mod f of x, because I'm mod f of x I'm considering. So now all it says is that this is the, this gives me supremum. This is the norm infinity, and this area under the curve is what? Norm f1. And is it clear that area of this function has to be less than or equal to, suppose if I extend this function, supremum function, and if I look at this whole thing, this as the function, means f of x as the supremum of f as the constant function, if I consider, then area under the curve is less than or equal to this, because it's the base length is 0, 1 multiplied by the subnorm of f. That has to be bigger than integration of this. Is that clear? Geometrically, can you see? Right. If you want to see rigorously what is happening, you write integration of mod f dx, but mod f of x has to be less than or equal to same thing, subnorm of f, means the infinite norm of f, that you can replace inside, and that is just a constant number you can push out, and what you get is the integration of the function from 0 to 1. That integration is just 1. So now we'll, yeah, what about the other one? I'm clearing it out. So what about the other one? This is a continuous functions on the compact set. So supremum is actually attained. So maximum of the function, can it be less than or equal to some constant times integration of the function is the question. Yeah. Who has the answer? So what do you think, first of all? Is it, can we able to find out a C2? What do you think? Are you able to find out or not? So this side is the maximum of the function, and the right hand side is the area of the function. So area of the function has nothing to do with the maximum. You can, as long as the base is small, you can have a very tall function, but still the integration can be as small as you want. Are you understanding this part? Good. Once with this intuition, of course, you can go ahead the way that you want. Now we are actually now trying to say that this is not true. That means I go back to the same principle that for all natural numbers, I should produce a function f such that this inequality is not true, which is same as saying I have C2, sorry. So n times norm f1 is not satisfying, so it is strictly less than norm infinity. Is that what we want to show? Yeah. So which one is easy to do? You can now think of. Okay, you can make. So now this is choices in our hand. What kind of f that you want to pick so that it is easy for you to make one of them, one of the norms on the inequality to be 1. Then it is easy to find out. Okay. So I'll suggest, suppose if I want looking for this one norm is 1, then the inequality just becomes n bigger than or n is less than norm infinity. So what are the functions for which you know the area under the curve is 1? So area under the curve, I want it to be 1, but the supremum is as big as I want. Suppose if I want my supremum to be n, can you think of a continuous function? Whose integration is that? Easy thing. Among the graphs which are easy, you can actually think. So on 0 and 1. I want the supremum has to be something like this number. But the area has to be small. So maybe I will do like this. So this height is something whatever you want. But this area you want it to be 1. But the inequality suggests me that suppose this is going to be 1 area. So it is n is bigger than subnorm of f. So maybe I will consider this sup is n plus 1. So that suggests what is the base here I should take it. And rest of the place I will take it as 0. Then it is a continuous function. Do you think you can fill up the rest of the details? You need to find out what is this. It's a triangle. Area you can easily find out. 1 by 2, this height and this. Okay. So fill it up. So it's going to be, if you have done, it's easy. Can you tell? Jayant, what should be this point?
1 by n plus 2.
1 by n plus 2. I want the integral has to be 1.
Okay. 2 by n plus 1.
2 by n plus 1. Just check. Yeah, this into this you will multiply, you will get 2, and 1 by 2 you have to multiply, so I will get 1. That's it. You're done. Okay, so write this function, and that's an example. So given any natural number, I will create, this is the function, this is my function. So I just put it in green. So this is my function. The function is from 0 to 2 by n plus 1. This is the function. You can write the function, and then from n 2 by n plus 2 to this one, it's 0. Of course, you can avoid all the things like what happens n equal to 1 case. It is just 1. It will go up to this place. Okay. Right. So what is the conclusion? So this norm 1 and norm infinity are not equivalent. These are not equivalent on C of 0, 1. I just give you a small exercise. If you understood everything, check the same thing. What happens? It is just trivial. You may think it is because of some 0, 1 is happening. No, even if you consider some closed interval AP, the same thing will work out. So these two norms are not equivalent. Did they write? So here also, the previous thing we are concluding, these two norms are not equivalent. Right. Now, we want to look at some more quick consequences of these equivalent norms, and we'll also come back to whatever examples that we have done. Number 1, suppose on X, if I have two equivalent norms, and I consider the following. So X sorry. So norm 1 and norm 2.
are equivalent on X, then first thing by the definition, it's the, so they are same topology. The induced topology is same. But there are other notions we defined using the norm. What can you say about Kashi? Suppose Xn is a sequence, is Kashi with respect to say one norm. Can you see that it is also Kashi with respect to the other norm? Look at the definition of norms being equivalent. Given epsilon, xn and xm are closer in one norm, but that is less than or equal to some c to constant times of x1, that's xn xm, with respect to some other norm. So there is a lower part you can use to conclude that. So this is actually same as saying it is Kashi with respect to norm also. Can you also conclude the same thing? What is the next thing that we can conclude? So Kashiness doesn't change with respect to these equivalent norms. If it is Kashi with respect to one, it will be Kashi with respect to other. What is the next thing? Convergence. Is that also immediate? Okay. Right. I'll ask also another question. Suppose A subset of X is bounded, again with respect to one norm. Can you also conclude the same? A is also bounded with respect to other norm? Yes. So A is and if say A is A. Suppose if X is Banach space, can you see it is also Banach space with respect to the next one? I'm clearing it up. Yes. All that I need to check is that whether every Kashi sequence converges, completeness. But Kashi, if it is with respect to one norm, it is also Kashi with respect to other norm. But in one norm, Kashi implying convergence, and hence equivalent to that convergence on the other norm also. Hence you get. So this is also. So X is one of these space with respect to the other norm. Okay. So equivalent norms I can put in the following way. Equivalent norm preserves all the following. It preserves Kashiness, convergence, boundedness, completeness, in fact the topology itself. That's what it says. Okay. Now there is a quick side information. In fact, it's a exercise I will leave it for you to think. That suppose in the norm equivalent, I have only one side. What do I mean by that?
is this. Suppose if I have, this is the definition of equivalence, equivalent norms. Suppose I don't have both, I have only one bracket, one of these curl. Then what do you think will happen to all these properties? Is the question clear? That means I don't have C1 and C2. Maybe I could find out only a C1, or maybe I find out only a C2, which is equivalent to saying that suppose if I have only this I have, I don't have the other one. What kind of conclusions do you think you can make? Now it's open. I want you to possibly answer. What other things do you think will work out?
Like one implication will be
Yes. So if and only if you will not get it, but I want you to check for all of them. Suppose if a set is bounded with respect to, let's say 2 norm, will it be bounded with respect to 1 norm? Just say yes or no. Yes. Okay. Right. And if a sequence is converging with respect to 2 norm, do you think it will converge with respect to 1 norm? Chetan says no. Okay, I want you to check this. You look like just with the inequality, you will be able to do that. Same thing with Kashi. If this itself is Kashi with respect to the 2 norm, it will be Kashi with respect to the 1 norm. And so this is usually called as dominating. Okay, so the norm 2 dominates norm 1. So some of the things we can actually get it partially, if not if and only if few sides you can get it. And from this information, can you see the following? We have looked at certain examples, the LP spaces, and then C of 0, 1. You have said in the case of C of 0, 1, so this was, we have looked for this. We have said that norm F1 is less than or equal to norm F infinity. So I'm asking the question, what is this in terms of convergence? I'm asking the following question. So we have observed norm of this is less than or equal to this, and at least C of AB. In fact, nothing wrong even in a bigger space. You can actually say this, but let's keep it this way. Now I say the following: that suppose Fn converges to F in this norm. Can I conclude that Fn converges to F in this norm? Using this above inequality. Right. Now, I'll ask you the following, that what is the meaning of saying that Fn converges to F in this subnorm? Again, an exercise, something that you might have done. If you have not done, we can do it. It's same as saying in another language, whatever you learned, Fn converges to F uniformly. You all agree? In fact, it is if and only if. saying that Fn converges to F in supnam is same as saying that Fn converges to F uniformly. So all it's saying is Fn converges to F uniformly. It says that this converges in one norm, which is what is the meaning of that? Norm of Fn minus F goes to 0. But what is the definition of norm of Fn minus F? It is integration of Fn minus F. This x dx integrating from 0. So this goes to 0. And this is something you already know. If Fn converges to F uniformly, then the integration also, this converges. You have you come across this before? Fn converges to F uniformly. And what about integral of Fn converging to integral of F? Or at least in your probability theory, you might have learned this. Convergence in probability. So that's what it says. So this says that now this information. But the other way is not true. That's what, since it is not equivalent norm, this is not true. That means this convergence is stronger than this one. If this convergence is weaker. The right hand side one converging in probability, or whatever you called it as, that's a weaker notion than expecting a uniform convergence. Same thing you can deduce for the sequence space where one norm and infinite norm. If a sequence converges in uniform in supnorm, it doesn't mean that it has to. I mean, it will converge in one norm, but not the other. You can make these conclusions. Okay, more things you can see later. So check all this, whatever exercise that is left out, and I'll stop at this stage.